Hi class and welcome to 4.4. Today we're going to talk about introduction to related rates. So our next application of the derivatives will focus on two or more rates that are simultaneously changing. We call these types of problems related rates problems. So the first thing we're going to do is we're going to conceptualize how these two rates can coexist. So our first example, we're just going to look at all four of these shapes, and suppose water is poured at a steady rate into the containers whose shapes are shown. Sketch the graph of the height of the water versus time for each. Okay, well, if I'm looking at this first one, we have kind of like a rectangular shape here, like a box. So if I'm pouring water in there, it's going to go nice and steady. It's going to fill up at a nice even level. So that tells me that this is going to be linear, okay? Now, if I look at the next one, so it kind of looks like an upside down T. So it's going to probably, if you think about it, the water's going to pour in. So the height versus our time, okay? So it's going to go, it's a little bit more shallow, and then it gets really narrow, so then it's going to go up like this. Okay. And again, these don't have to be perfect. These are really just guesstimating what you think it's going to look like. So if you're watching from home, go ahead and try the next two and see how you do on them. Okay, welcome back. So let's look. So here's an I-shaped. So it's going to go a little bit like this. So it's a little bit more broad, then narrow, and then broad again. Okay. And now we have two circular things here. So we're going to go, it's going to fill up. It's a little bit more narrow, so it'll be a little bit more steep. And then it gets wider, so it'll flatten out a little bit. Okay. So the next important thing that we have to understand before we actually attempt some related rates is how do I write this mathematically? Because we're going to be needing to set up equations. So we're going to write the following mathematically. So John is growing at the rate of 3 inches per year. So here's a keyword, at the rate. So anytime you're seeing that rate, you should be thinking derivative. Okay, well, he's growing, so that means that's a positive. So how I'm going to write this then, and the letter here doesn't necessarily matter. I'm going to just say, because we're talking about his height, I'm going to call this DH. Now it is with respect to time. With related rates, we're always talking with respect to time for the most part. So DH dt is equal to 3. Let's go to the next one. My mutual fund is shrinking by 4 cents per day. Okay, so shrinking, okay, so that's a negative. For here, the cents per day, that lets me know we're talking about a rate, so I should be thinking about a derivative. Okay, so let's just say I go df dt is equal to negative 0.04. So go ahead and try C and D and see how you do. Welcome back. The radius of a circle is increasing by 4 feet per hour. So let's just say dr dt is equal to 4. Okay, and this one we have the volume of a cone is decreasing by 2 inches cubed per second. Okay, so then let's just say we go dv dt, and it's decreasing, so it's negative, so we got -2. Okay, so now we can start some examples. So we're going to scaffold these before we get into a little bit more complicated related rates problems. So the first thing we're going to talk about is a rectangle. When I'm dealing with related rates, one of the first things I'm always going to want to do is draw a picture. So I know with a rectangle in the first couple of examples we're doing are all shapes that we're familiar with, but when we get into more complicated word problems, sometimes it's not as easy to see what shape is going on, so you always want to sketch your figure. Okay, so I have a rectangle, and you only want to label information given. So I'm just looking at the rectangle is undergoing changes to its length and width. So I'm only concerned with its length and its width. Okay, so let's read the question. A rectangle's length is increasing at the rate of 2 inches per second, and its width is increasing at a rate of 3 inches per second. Find how fast the perimeter is changing at the moment its length is 10 inches and its width is 6. Okay, so the first thing I'm going to do is I'm going to figure out, okay, what information is given to me in this problem. So if I'm looking, I know the rectangle's length is increasing at a rate of 2 inches per second. Okay, well, we just practiced writing that. So let's just say, we're talking about length, so I'll just say dl dt, and it's increasing, so that's 2. Okay, so let's go to the next part. What else do we know? Its width is increasing at a rate of 3 inches per second. Okay, so let's go ahead and write that. So dw dt is equal to 3. Okay, we're going to diagnose the next part of this. Find how fast the perimeter is changing. Okay, so I need to figure out how fast is this perimeter changing. So that's going to be my find. So we'll just say dp dt. We don't know that. Okay, at the moment, its length is 10 and its width is 6. Okay, so length is 10, width is 6. So I'm going to go ahead and add that to my stuff that I already know. So its length is 10 and its width is 6. Okay. And again, if you don't want to use dl/dt or dp/dt, you could always use p prime, l prime, w prime, stuff like that. Okay, that's perfectly okay to use those variables. I would just stay consistent. Okay, so that's kind of the first 3 steps. So look at the information, draw your picture, and then figure out what is given and what do I need to find. So now the third step is I need to actually write an equation. Well, I'm talking about the perimeter and I'm talking about a rectangle. So then I'm going to use the equation of the perimeter of a rectangle. So the perimeter of a rectangle is equal to 2L plus 2W. So now we can go ahead and solve. Now remember, we're trying to find the rate at which our perimeter is changing, so I need to take the derivative of this equation. So I have the derivative, and now here's where that's implicit. I'm taking everything with respect to t, so it's just like when we learned implicit in 2.5. If I took the derivative of y, so let's say y squared, right, with respect to x, that was 2y dy dx. Okay, so it's the same thing here. So if I'm taking the derivative of p with respect to t, I get dp dt, because the derivative of p is 1. Okay, well, the derivative of 2L is going to be 2, but then, because it's 2 times 1, but then remember L with respect to L, so dl dt plus 2w, well, the derivative of 2w is 2, and then times dw dt. Okay, so now we can plug it in. So one of the key things with related rates is you don't want to plug anything in until you take the derivative. That's one of the most common mistakes with related rates. So write your information, draw your picture, write the equation, take the derivative, then plug in your information. Okay, so we need to find dp dt, so I'm just going to leave that. So 2 times dl dt, so dl dt is 2, plus 2, well, dw dt is 3. So this is equal to 10. Now again, I want to make sure I label. So this is going to be 10 inches per second. That's the rate at which it is changing. If I wanted to write a formal sentence with it, like if they said to interpret my answer, I would say the perimeter of the rectangle is increasing at a rate of 10 inches per second when L is 10 and W is 6. So again, using that NUT acronym, noun, unit, time. So again, the perimeter of the rectangle is increasing at a rate of 10 inches per second when L is equal to 10 and W is equal to 6. Okay, so let's go to B. So now the rectangle's length is increasing by 3 inches per second and its width is decreasing by 2 inches per second. Find how fast the area is changing at the moment its length is 10 and its width is 6. Okay, so we have the same picture, so I don't need to redraw my picture. Okay, so again, I'm going to figure out my given. So the rectangle's length is increasing by 3. So dl dt is equal to 3. Its width is decreasing by 2. So dw dt is equal to -2. This information is staying the same. The length is 10, the width is 6. Okay, but now this time, they're asking us how fast is the area changing. So that's a little bit different. So I need to find dA dt. Okay. Well, let's think about that. Now I'm going to write that equation. Well, if I'm trying to figure out how the area is changing of a rectangle, I need the equation of the area of a rectangle. So the area of a rectangle is length times width. Okay, and now I'm going to go ahead and solve. So again, we're finding dA dt. So that means I need to take the derivative. So I have dA dt equals, now L times W, that means I'm having to use my product rule. So the derivative of the first, so dL dt times the second, plus the first times the derivative of the second. And then again, I'm going to go ahead and plug everything in. So I have dA dt equals, okay, 3 times 6 plus L times -2. Oops, we know what L is. L is 10. Okay, so then this is equal to -2. And since I'm talking about area, it's going to be inches squared per second. If I were to formally write this, I would say the area of the rectangle is decreasing at a rate of 2 square inches per second when L is 10 and W is 6. Okay, so let's go ahead and try a new one. So this time we're going to be dealing with a right triangle. So a right triangle has sides whose lengths are changing. The short side is increasing at 3 inches per second, and the long side is decreasing at 5 inches per second. Find the rate of change of the area of the triangle. At the moment, the short side is 30 and the long side is 40. Okay, so first thing I'm going to do here is I'm going to draw a picture. Well, luckily I'm just dealing with a right triangle. That is pretty easy to draw. Okay, so they're labeling everything as short side and long side. So I'll do long side. Here's my short side. Okay, so now let's go ahead and figure everything out. So I need to find the rate of change of the area of the triangle. Okay, so I'm finding the area. So dA dt. At the moment, the short side is 30 and the long side is 40. Okay, so we know S is 30, L is 40, and then of course from the original part of it, the short side is increasing at 3 inches per second and the long side is decreasing at 5 inches per second. So again, we'll write that. So I'll just say ds dt is equal to 3, and dl dt is equal to -5. Okay, so I need an equation. Well, since I'm dealing with the area of a triangle, that's the equation I'm going to write. So the area of a triangle is 1/2 base times height. Well, in this case, my base is S and my height is L. That's why it's important to label. Okay, so now we can go ahead and take the derivative. So I have dA dt equals, now I'm always putting that constant on the outside. So there's a 1/2 times S times L. So I have to use the product rule, but I'm putting my constant on the outside. Okay, so then I have the derivative of the first times the second plus the first times the derivative of the second. Okay, so now again, all I have to do is plug in my stuff. So again, I'm trying to find dA dt, so 1/2. So ds dt is 3, L is 40, plus S is 30, times dl dt is -5. Okay, well, plugging that all in, and this is why I do the 1/2, because it's just easier for mental math. So I have 120 plus a -150, so that gives me -30 times 1/2, which gives me -15. And again, a label is important. So we're talking about inches per second, and then we're finding the area. So it's inches squared per second. If I were to formally write this, I would say the area of the triangle is decreasing at a rate of 15 square inches per second when S is 3, when the short side is 3 and the long side, when the short side is 30 and the long side is 40. Okay, let's go to the next one. So now they're saying, how fast is the hypotenuse changing at the moment the short side is 30 and the long is 40? Okay, well, so now we have a different, so it's the same picture. We're still talking about a rectangle, but now we've introduced the hypotenuse. So that's why I'm going to redraw it and just make sure I have my H here. Okay, so let's go ahead and figure out, okay, so our givens are going to be the same. So my S is 30, my L is 40, ds dt is 3, and dl dt is -5. What's changing is I want to figure out, well, how fast is the hypotenuse changing? So I need to find, we'll just call this dH dt. Okay. Now I need to write an equation. So if I think about it, I need an equation to deal with the hypotenuse. Well, if I have a right triangle and I need something with the hypotenuse, a famous theorem should be coming to mind, hopefully. And that would be your Pythagorean. So I have L squared plus S squared equals H squared. So again, now I'm going to need to take the derivative. Okay, so I have 2L dl dt plus 2S ds dt equals 2H dH dt. Okay, so now we're going to plug everything in. So if I look here, I have I notice here they all have a 2. So if you don't want to deal with the 2, you could take all those 2's out. Okay, so I have 2 times L, which is 40. Then I have dl dt, which is -5, plus 2 times S, which is 30, ds dt equals 2, H. Well, they didn't give us H. Huh. Does that mean we can't solve the problem? Hopefully you are saying no here. So remember, I need H. Well, I know L is 40 and S is 30. So that would mean H is 50. And what you could have done the Pythagorean theorem, 30 squared plus 40 squared equals H squared. Or remember your Pythagorean triples, 3, 4, 5. So this would be 30, 40, 50. So that's 50, and then dH dt is what we're trying to find. So this is a hidden given. Okay, so now we just need to figure this out. So I have negative 400 plus 180 equals 100 dH dt. So negative 220 equals 100 dH dt. Well, to get dH dt by itself, I'm going to divide. And negative 220 over 100. So dH dt is negative 11 fifths. If it was an actual AP exam, you just leave it as negative 220 over 100. That's perfectly fine. Now I got to make sure I'm labeling it. So I'm talking about a hypotenuse, which is a length. So that will just be inches per second. And if I was formally writing this, I could say the hypotenuse of the triangle is decreasing at a rate of 11/5 inches per second when S is 30 and L is 40. So again, with that NUT acronym, you'll notice that you get pretty good at writing these. Okay, so ideally, this is one that I would like you to try on your own, dealing with a cylinder. Okay, so pause the video, come back and let me know how you did. Welcome back for those that pause. So example 5, a right circular cylinder has a height and radius whose dimensions are each changing. The radius is growing at 2 feet per minute and the height is shrinking at 3 feet per minute. Find the rate of change of the volume of the cylinder at the moment the height is 10 and the radius is 8. Okay, so I'm drawing it. I have a cylinder. So looking a little something like this. Again, your pictures do not have to be perfect. I have a height and I have a radius. Okay, so let's look at our givens. I know the radius is growing at 2 feet per minute. dr dt, there we go, is 2. Okay, I know that the height is shrinking at 3 feet per minute. And then find the rate of change of the, find the rate of change of the volume of the cylinder. So I'm trying to find dV dt when the height is 10 and the radius is 8. Okay, so now I need an equation. Well, I'm trying to find, the rate of change of the volume of a cylinder. So what is the volume of a cylinder? So that is V equals pi r squared h. And again, if you don't remember these formulas, there is on Schoology in the Review, there's a great section where there's a ton of geometry formulas that you should know because we do use a good amount in this section. Okay, so now let's go ahead and solve. Well, I need to find dV dt, so I'm going to take the derivative. So dV dt. Well, remember, pi is a constant, so I'm taking pi out. So I got to take r squared times h, so I have my product rule. So 2r dr dh, or dt, times h, plus r squared times dh dt. Okay, so now I am going to plug stuff in. So I have pi times 2. Well, r was 8. Whoops. Dr dt is 2 times dr. Okay, goodness gracious. Let's start over. 2 times r times dr dt, there we go, times h plus r squared, okay, so that's 64, times dh dt, which is 3. Well, oh no, and shrinking, oops, that should be -3. There we go. Sorry about that. Okay, so now when I plug this in, I get pi times, well, 320 minus 192. So that's going to give me 128 pi. Now I'm talking about volume, so it's going to be feet cubed per minute. Perfect. Okay. Again, yeah, and you want to keep the pi in there. Okay, so last one. The radius is decreasing at 4 feet per minute, and the height is increasing at 2 feet per minute. Find the rate of change of the surface area of the cylinder at the moment the height is 10 and the radius is 8. Okay, so again, let's look what we know. So dr dt, the radius is decreasing at 4 feet, so -4. Caught it the first time this time. dh dt is equal to 2. Find the rate of change of the surface area, so we'll say ds dt. At the moment the height is 10 and the radius is 8. Okay, well now again I need an equation. Again, if you don't remember, just go make sure you go look it up. So this is 2 pi r squared plus 2 pi r h. And for me personally, I'm going to take that 2 pi out. So 2 pi r squared plus rh. And again, the reason why I didn't do the r with that is simply because I'm just setting myself up for a nice derivative. Okay, so now let's go ahead and find, and again, this is my surface area. There we go. So ds dt is equal to 2 pi. Okay, well, the derivative of r squared is 2r dr dt plus, well, now I'm taking the derivative of RH. Okay, well, that's your product rule. So the derivative of R is dr dt times H plus the first times the derivative of the second. So that is dh dt. And now I get to plug everything in. So I have 2 times R times dr dt plus, again, I have -4 times H plus R times 2. Sorry about that. Okay. Now, if I was at an AP exam, I would leave my answer like that and label it, but I have calculated this out. This is -176 pi. And again, because I'm talking about surface area, I have feet squared per minute. Okay. And then again, if I was writing it, I would say the surface area of the cylinder is decreasing at a rate of 176 pi square inches per minute when H is 10 and R is 8. So that's the first part of related rates. This is 3.4. We'll continue these notes for 3.5. Have a wonderful day and message me on Schoology if you have